In this video, we are going to talk about utilizing the phasors for the parallel RLC circuit with an AC source. The figure shows a parallel RLC circuit with a voltage source. The voltage source drives the source current, which then divides at the junction into the resistor current, the inductor current, and the capacitor current. As previously discussed, the resistor current is in phase with the source current. The inductor current is out of phase with the source current and leads by 90 degrees. Again, the reason is that as the voltage is induced in order to oppose the change in the magnitude of the magnetic field, due to the incident current. The inductor voltage is in phase with the inductor current and leads the source current by 90 degrees. The capacitor current is also out of phase with the source current and lags by 90 degrees. As we previously learned, as the current increases through the capacitor, charges accumulate at the plates and the capacitor voltage increases. The current decreases as more and more charges fill up the plates and the capacitor voltage decreases. The capacitor voltage is in phase with the capacitor current. We use Kirchhoff's junction rule to sum up the currents. However, since phasors are composed of both amplitude and phase angle, the currents add up in squares as shown. Since the inductor and capacitor currents are out of phase by 180 degrees, we rewrite the expression as shown. The phase angle is similarly computed as in the previous lesson, but now in terms of the currents. It will then be elementary to solve for the resistor, inductor, and capacitor voltages. If we rewrite the derived expression for the current in terms of the voltage and impedances, we get the following expression. Since all voltages are equal to the source voltage in the given circuit, we are left with the expression as shown. Plugging in the resistance and reactances, we get the following equation. We now define new parameters that should make things easier to analyze the parallel RLC circuit. These are the admittance, conductance, inductive susceptance, and capacitive susceptance. We can then write the following expressions for these new parameters as shown. Now that we have computed for the phasor magnitudes, let's see how the phase angles are related for these reciprocal parameters. We know that in series RLC circuit, the phase angle is computed in terms of the impedances. Note that we can graphically represent tangent theta in terms of a triangle where the hypotenuse is the total impedance, the adjacent side is the resistance, and the opposite side is the reactance, and the phase angle is between the impedance and the resistance. In the parallel RLC circuit, we have the admittance expression given by the equation as shown. By inspection or comparison, we obtain the expression for the phase angle to be equal to the given expression with a negative sign. This negative sign is due to the fact that when we take the reciprocal of the reactances, the imaginary number becomes negative since 1 over j equals negative j. We can then depict the admittance triangle as shown, where the hypotenuse is the admittance, the adjacent side is the conductance, the opposite side is the susceptance, and the phase angle to be between the admittance and the conductance. I hope you've learned how to manage parallel RLC circuits. More realistic circuits definitely include a combination of both series and parallel components. Check out more examples provided and try to answer some of them before going through the video examples. We'll be discussing power in AC circuits next.